Hello everyone, welcome to my channel. In this lecture, we are going to cover the topic joint distributions in detail. So this topic it is going to be very helpful and beneficial for all those students who are working in the area of artificial intelligence, machine learning, who all are having the probability and the statistics course at the graduate and the undergraduate level. So this video it is going to be very beneficial for all these students. In this video, we are going to cover the topic joint probability mass function, density function, marginal density, condition for independence, how to check whether the two random variables are independent or not, the expected value, covariance between two random variables, and at the end of the video, I'll give you two questions for practice. So now, if you are not confident enough in the concept of a random variable and the probability mass function and density function in the context of a single random variable, so I suggest you to first watch these videos based on the topic random variable, probability mass function and probability density function in the context of a single random variable. I'll put the link on these videos in the description box. Please find these links and go through these videos first. Only then you will be able to understand the concept of this joint distribution more clearly. Okay, let's start with the concept of the joint distribution in detail. So the question arises, why do we need to study joint distribution? Basically, what happens in real life that sometimes we may wish to study two random variables or more than two random variables simultaneously. So in these cases, the concept of the joint distribution come into picture. So say for an example, if we want to check the condition of the yield of wheat. Now this yield of wheat, it depends on the several factors. We have the variety of factors. It depends on the type of soil. It depends on the climate condition, that is the weather condition. It depends on the this is the weather condition. It depends on the nutrients availability or the water availability, so we can write this is nutrients availability. And what else? It depends on basically it depends on the method of harvesting. So it depends on the several factors, variety of factors. So whenever we need to study, so this is the method of harvest, whenever we need to study all these factors simultaneously, that how these factors is going to affect the yield of wheat, so that means the concept of the joint distribution come into picture. Now to keep it more simple, we'll take just two random variables. If we are taking the one random variable capital X as the temperature and capital Y as the sales of ice cream. So this is other example. So we may wish to study that how these two random variables vary each other. That means how these two random variables vary. That means with the increase in temperature, is the sales of ice cream increases, or with the increase in temperature is the sales of ice cream decreases. So that means how these two random variables vary together. We may wish to study these type of questions, or we may wish to find out what is the average sales of ice cream at a specific temperature, say at temperature 45 degrees Celsius. So these questions can be answered with the concept of this joint distribution. Okay, now what exactly is the joint distribution? Basically, joint distribution. So whenever we need to study two random variables together, so this is a concept of a bivariate random variable, because here we have two random variables. So this is bivariate random variable. Now, if both these random variable, we are taking two random variables X and Y here. So if both the random variables are discrete, then this is a case, that means the function defined by these two random variable, it is denoted by f of xy, where this capital X and Y, it denotes the random variable, and this small x comma y, It is the values that this capital X and capital Y is taking. Okay, so or in some books it is simply referred to as f of x comma y. Now, if both these random variables are continuous, again the notation is same, that is it is represented by fxy of x comma y, or simply you can write this as f of x comma y. So for the discrete case, this joint distribution, it is known, that is this function, it is known as the joint probability mass function. So this is the joint probability mass function. And for this continuous case, this is known as the joint probability density function. So now we'll discuss both these functions, that is joint probability mass functions and joint probability density function, in detail. So joint probability mass function, this is a function when both the random variables x and y are discrete. So if both are discrete, then the function defined by this, it is given by joint probability mass function, and we denote this function as fxy of x comma y, or we simply write this as f of small x comma y. Now what does this f of x comma y represent? F of x comma y, it represents the probability at x is equals to x and y is equals to y. So that means since x and y are discrete in nature, so x and y, they are taking the distinct values. So this fxy, it is denoting the probabilities at x is equals to x comma y is equals to y. Now what is the necessary and sufficient condition for a function to be a joint probability mass function? So sufficient condition for a function to be a joint probability mass function. So I'm simply writing joint probability mass function, that is joint PMF. Okay, so the first condition for a function to be a joint probability mass function, since f of xy, it is simply representing the probability at x is equals to x comma y is equals to y. So since probabilities, we know that probabilities are always greater than equals to 0. So the first condition is probabilities, that is f of x comma y, this is always greater than equals to 0 for all the possible values of x and y. And the second condition, when we sum up all the probabilities over the possible values of x and y, that is sum over x and sum over y of this function, that is of all the probabilities, fxy is nothing but the probabilities at x is equals to x and y is equals to y. So when we sum up over all the values of x and y, if it is equals to 1 and if these two conditions are satisfied, then we say that the function is nothing but the joint probability mass function. Now we'll understand the concept of the joint probability mass function with the help of an example. Suppose we have a random experiment of tossing of two coins. So we have the experiment of tossing of two coins. Now for this random experiment, the corresponding sample spaces that on both the coins, if head turns out, on the first coin head turns out, on the second tail turns out, so the outcome will be head tail. Then we have tail head on the first, we have head on the second tail, head, and on both the coins if tail turns out. So this is the corresponding sample space of the random experiment of tossing of two coins. Now if we are denoting the two random variables x and y as, let x, it denotes the number of heads for this experiment of tossing two coins, and y as the number of tails. So if we look at the possible values of x and y, so number of head for these sample space, the number of head, it could be 0 if the outcome turns out. It could be 1 if the outcome head tail or tail head turns out, and it could be 2 if the outcome head turns out. So x can take values, x assumes the values 0, 1 and 2. Similarly, y, it assumes the value, since y denotes the number of tail, so it assumes the value 0, 1 and 2. Now, what is the joint probability mass function for this? So for this, if we are taking this as x and this as y. So x is taking values 0, 1, 2. So write this as 0, 1, 2 because they are taking distinct values, discrete values. We have the values as 0, 1, 2. There is no such value in between 0 and 1. That means it is not taking values or not assuming values in an interval. It is taking values at these points, that is 0, 1, 2. And y is taking values 0, 1 and 2. Right now, when x is 0, when y is 0, what does it mean? That 0 number of head and 0 number of tail. So what is the probability of getting 0 number of head and 0 number of tail? So the probability of getting 0 number of head and 0 number of tail, that means at the same time we do not have any such outcomes for this experiment. So the probability is going to be 0. Then 0 number of head and 1 number of tail. There is no such outcome here. So again the probability is 0. 0 number of head, because here x represent the head and y represent the tail. 0 number of head and 2 number of tails. Here we have this outcome, that is tail, where we have 0 number of head and 2 number of tails simultaneously. So one such outcomes out of 4 outcomes, we have one outcome here. So the probability will be 1 by 4. Then we have 1 number of head and 0 number of tail. So that means what is the probability here? There is no such outcome where we have 1 number of head and 0 number of tail. So this is going to be 0. 1 number of head and 1 number of tail. So here we have two outcomes, head tail and tail head. In both these outcomes, 1 number of head is there, 1 number of tail. So this becomes 2 by 4. Out of 4 outcomes, 2 outcomes where we have 1 number of head and 1 number of tail. And 1 number of head and 2 number of tails together simultaneously, it is going to be 0, because there is no such outcome where we have 1 number of head and 2 number of tails. Then we have 2, that is 2, 0, 2 number of head and 0 number of tail. So if we look at this sample space, so 2 number of head and 0 number of tail, again we have one outcome here, that is head, head. So this is 1 by 4. 2 number of head and 1 number of tail, this is going to be 0. 2 number of head and 2 number of tail, this is going to be 0. Now, if we want to check whether this is a correct probability mass function table or not, it is the correct joint probability distribution table or not, for that, what are these? So these points, basically if we look at these points, that is this one, this one, this one. So what does these represents? These represents the probabilities. So these represent, that means this first point, the first one, it is representing the probability at x is equals to 0 and y is equals to 0. So if we look at this, that is this point, it is nothing but probability at x is equals to 0 comma y is equals to 0. What is this? This is nothing but probability at x is equals to 0 and y is equals to 2. What is this point? This is probability at x is equals to 2 and y is equals to 2. So these all are representing the probabilities. Or in simple words, what is this one? We can simply write this as function at x is equals to 1 and y at 2. So f at 1 comma 2 we can write it as, or we can simply write it as probability at x is equals to 1 comma y is equals to 2. Now, if we want to check whether these all, this is a valid joint probability mass function table or not. So for this, first we need to check the first condition. The first condition is that all the probabilities, or simply fxy, this must be greater than equals to 0 for all the possible values of x and y. So here the possible values of x and y are 0, 1, 2, y as 0, 1, 2. Now the corresponding probabilities, they all are greater than equals to 0. That means first condition is second satisfied. Now the second condition, what is the second condition? Summation over all the values of x, that is sum over all the values of x. Here x is taking values 0 to 2. Sum over all the values of y, y is taking values from 0 to 2. When we add all these probabilities, that is f of x comma y, is it equals to 1 or not? So we have to check this. So basically we just have to add all these probabilities. So this is 0 plus 0 is 0, then plus 1 by 4 is 1 by 4, plus 0 it is 1 by 4, plus 2 by 4 it is 3 by 4, plus 0 3 by 4, plus 1 by 4 becomes 4 by 4, which is 1, plus 0 is 1 and plus 0 it is 1. So that means the sum of all the probabilities over the possible values of x and y, it is equals to 1, and the two conditions are satisfied, and hence it is a valid probability mass function. Now let's visualize this example with the help of this figure. So here, if this is our x-axis, so let this is our x-axis, the values that this capital X is taking, and this is y-axis, that is the value this random variable capital Y is taking. So here X is taking value 0, 1 and 2. So let this is point 0 on the X scale. So this is 0, 1 and 2. And on the y scale, again y is taking value 0, 1, 2. So this point is 0 for the y, this is 1 and this is 2. Now, the corresponding probabilities, because it is simply taking values at 0, 0, 0, 1, 0, 2 and all these points. So, at x is equals to 0 and y is equals to 0. So, this is y is equals to 0 and x is equals to 0. The probability is 0. So, it is simply this point. Then we have this scale, basically this line, this is for the function that is f of x comma y. So this basically it represents the height. Okay, now when x is 0, y is equals to 1. So which point corresponding to this x is equals to 0 and y is equals to 1? X is 0 and y is equals to 1, that is this point. So this is the point here, that is this is the point when x is 0, y is 1. Again the probability is 0, so it is simply this one. When x is 0 and y is equals to 2, the corresponding probability is 1 by 4. So when x is 0 and y is 2, so this red line, it represents the function, that is the probability. So it is 1 by 4. That means height it is taking from this point to this point, it is 1 by 4. Then at x is equals to 1, this is x is equals to 1 and y is equals to 0. So at x is equals to 1 and y is equals to 0, this is the point, that is x is 1 and y is 0. Probability is 0, so it is simply this one. At x1 and y1, that is it is equals to 2 by 4, corresponding to 1 and 1. So that means this is the point at x is equals to 1, corresponding to x is equals to 1 and corresponding to y is equals to 1. So the probability is 2 by 4. So this height, which is corresponding to this axis, that is f of x comma y. So this is the probability at this point. Then we have at x is equals to 1 and y is equals to 2. So x is equals to 1 and y is equals to 2, it is 0. So x is 1, y is 2, it is this point, so it is 0. Then x is 2, y is 0. So x is 2 and y 0 is this point. So that means here the probability is 1 by 4. So here we have this line, that is this is 1 by 4. Then x is 2, y is 1. X is 2, y is 1 corresponding to this point. The probability is 0. And x is 2, y is 1. It is corresponding to this point. The probability is 0. So when we add all these probabilities over these points, it is coming out to be 1, and all these probabilities are greater than equals to 0. Hence it is a valid probability mass function. Now coming to the joint probability density function. So joint probability density function, when both the random variables x and y, it is continuous. So if the variables are continuous, so the function given by this, that is fxy of x comma y, or simply f of x comma y, this function, it is nothing but the joint probability density function. So for these, because x and y, they are continuous, so they are taking values in interval instead of taking or assuming value at the distinct point, as we have the case in the joint probability mass function. Here this x and y, they are assuming values in an interval, that is over a set of real numbers, they are assuming all values. So for this, what is the necessary and sufficient condition? So the necessary and sufficient condition for a function to be a joint probability density function. So this is joint probability density function. Now What is the necessary? The first condition, because fxy, this is representing the probabilities over an interval. So that means the first condition, since these are the probabilities, so fxy, this is going to be greater than equals to 0 for all the x comma y belongs to real number. So jitne bhi real numbers values hai, that means it is going to be greater than equals to 0. And the second is that instead of, because in the case of a discrete we have used summation, because there we have the values at the distinct points, here we have the values over the interval. So instead of summation we are going to take the integration, that is for the x it is going from minus infinity to infinity, for the y it is going from minus infinity to infinity. And what is the function? The function is f of x comma y. Integrate with respect to y, then with respect to x, or you can also change the order of integration, that is first with respect to x and then with respect to y. And if this double integral it is equals to 1, then we say, if these two conditions are satisfied, then we say that the function, it is a joint probability density function. So in the case of a joint probability density function, if we are saying that probability x is in between a is less than equals to x is less than equals to b, and y it is c is less than equals to y is less than equals to d. So what is the probability whenever x is in between a and b and y is in between c and d? That means x is taking all the values in the interval a to b, and y is taking all the values in the interval c to d. So this is nothing but double integral. X is taking values from a to b, y is taking values from c to d, and the function, that is the joint probability density function, integrate with respect to y first, then with respect to x, it is equals to 1. So this probability, it is given by this double integral. Now let us understand the concept of the joint probability density function with the help of an example. So here we have two random variable. First is x. Here this capital X, it is denoting the person's blood calcium level, and capital Y, it is denoting the blood cholesterol level. Okay. Now the probability density function, that is fxy, this is given as this constant k whenever x is in between 8.5 to 10.5. So if we have, let this is our x scale. So if you look at this one, let this is our x scale and this is the y scale. So this is x axis, this is y axis. So that means if you look at this figure, although this is not corresponding, completely corresponding, just to visualize this example, that is this point for this x scale, let corresponding to this one, this is from x is going from 8.5. So let this point is 8.5 and this point it is, let it be 10.5. So that is, it is taking all the values from 8.5 to 10.5. Now then y is taking values from 120 to 240. Let this is the origin. So this is for the y scale. So y is taking values this 120 to 240. So this point is 120 and this is 240. So if we plot this in the xy plane, so if we are taking, let this is our x and y plane. So x is taking values from 8.5 to 10.5 and y is taking value from 120 to 240. So that means it is in between these values. So that is for all these values, all the points in between or within this domain, that is where x is in between 8.5 to 10.5 and y is in between 120 to 240. That is for all the points in the domain. Here it is taking all the values within this domain, right? The function, that is the probability, it is given as a constant. So constant, this height, it is representing the probability, that is f of x comma y. So that means this height for all the points. So this height for all the points in within this domain, that is from x is going from 8.5 to 10.5, y is from 120 to 240. For all this domain, it is going to be k. That means this height, it is representing the probability. Since it is for all the domain points, it is not at the distinct points. So here we have something like this one. So this is just a visualization. Now the question is, find the value of k. As you see here, both x and y are continuous random variable, and for the case of a continuous random variable, we'll use integration instead of the summation. Now we'll solve this question. So basically, the function, that is the probabilities, it is given by probability density function. It is given by k whenever x is in between 8.5 is less than equals to x is less than equals to 10.5, and y 120 is less than equals to y is less than equals to 240, and this is 0 elsewhere. So this is a probability density function, and we have to compute the value of k. Since it is a valid probability density function, so by the second condition of the probability density function, that integral over x values and integral over y value. So what is our x value? X, it is going from 8.5 to 10.5, and what is the y value? It is going from 120 to 240. So better if you plot the graph for this one, that is the domain where this x and y are taking values. So if this is our x-axis, this is our y-axis. So this is x, this is y, and this is 8.5, this point is 10.5, this is 120, and this is 240. So that means x is taking values within this 8.5 to 10.5, and this is y is taking values 120 to 240. So within this domain, we have to integrate the function f of x comma y. So the function is k, that is f of x comma y, this is k. So first integrate with respect to y, then with respect to x, and this is equals to 1. So this is equals to, when we integrate with respect to y first, and since k is a constant, we can write this as this outer limit for x as it is 8.5 to 10.5, and first integrate with respect to y. So since k is a constant, it is k, and the integration with respect to y, it is simply y, and the limits for this y as 120 to 240, and then integrate with respect to x, which is equals to 1. And this is equals to integral 8.5 to 10.5. When we plug in the value of this y, that is first plug in y is equals to 240, then 120. So this k as a constant, can I take this constant outside of this integral, and this becomes 240 minus 120. This is simply 120 dx, which is equals to 1, and this is equals to k. Now integrate this 120 with respect to x, so this becomes 120x, and take the limits from 8.5 to 10.5, and this is equals to 1. So this is equals to this 120k. I can take this 120k outside, and when we plug in x is equals to 10.5 minus 8.5, which is equals to 2, that means 120k multiplied by 2, it is equals to 1, and from here the value of k, it is equals to 1 by 240. Now instead of integrating, because here x and y limits are the constant limit, so basically what we need to find out, we have to find out the area within this integral. So if you look at this, that means this point, it is from 8.5 to 10.5, and this is 120 to 240. So we can simply find out the area within this domain. So the area, basically this k as it is, and area within this domain, that is integral 8.5 to 10.5, 120 to 240 dy dx, it represents the area. So write this k as it is, and what is the area within these limits? So area, it is nothing but this width, it is equals to 10.5 minus 8.5, which is 2, and this is 120 to 240. So the this height, it is nothing but 120. So 120 multiplied by 2, that is this area, it is 240. So basically we simply write it as k into 240, which is equals to 1, and from here k is equals to 1 by 240. It is only when the limits of x and y are the constant limits. So here the value of k, it is equals to 1 by 240. Okay, now coming to the concept of the marginal densities. So marginal densities are basically the individual densities of the random variable x and y. So we'll start with the marginal density. For the marginal density, again we have for both the cases discrete and continuous when x and y both are discrete and when x and y both are continuous. So suppose we have, let x and y be two-dimensional discrete random variables, okay, and with their joint probability function, it is given by fxy of x comma y, or simply this is f of x comma y. Then the individual density, so this basically f of x comma y, it represents the joint density, joint probability mass function in case of a discrete random variable. So this is the joint PMF, and the joint PMF, if it is given by f of x comma y, then the individual density, it is given by fx of x. So this individual density, it is for x. So this fx of x, it is nothing but the marginal density of x, and this is the marginal density of x. And what is fy of y? This is marginal density of y. Similarly, if x and y are continuous random variable, x and y, this is continuous random variable with their joint probability density function, it is given by fxy of x comma y, or simply f of x comma y. So this is the joint probability density function, and then the individual densities of x and y, it is known as the marginal densities of x and y respectively. So fx of x, this is the marginal density of x, and fy of y, this is the marginal density of y. Now, what are the computational formulas for this marginal densities? So in case of a discrete, so here we have discrete. In case of a discrete random variables x and y, then fx of x, this is given by, for the case of a discrete, we always use summation. Okay, so whenever we are finding out the marginal density of x, take the sum over all the values of y. And what is the joint probability function? This is f of x comma y. So take the sum over all the possible values of y, and this is f of x comma y, and this is fy at y, that is the marginal density of y. This is, here we are finding out the marginal density of the random variable y. So take the sum over all the possible values of x, and this is the joint probability mass function, that is f of x comma y. Now, for the case of a continuous, when x and y be two-dimensional continuous random variable, then the individual densities, that is fx of x, since it is a case of a continuous, so we'll use integration. Now, integration over possible values of y. And what is the joint probability density function? This is f of x comma y. So simply integrate, that is f of x comma y. Here we are finding out the marginal density of x, then integrate with respect to y over the values of y. And what is the marginal density of y? Marginal density, that is individual density of y. So this is taking integral over x and integrate with respect to x only, and the probability, joint probability density function is f of x comma y. So this is for the case of continuous. For the case of continuous, we'll use integration. For the case of discrete, we'll use summation. If we are finding out the marginal density of x, then take the summation over y values in case of discrete, and take the integration over y values in case of the continuous. Now, let us look the concept of this marginal densities with the help of an example. We are taking the same example. So the example here, the random experiment E, it is nothing but the tossing of two coins. So this is the random experiment, tossing of two coins. Here x denotes the number of heads. This is number of heads. Y denotes the number of tails. So number of tails. So x and y both are discrete. So this means x is taking values 0, 1 and 2, and y is taking values 0, 1, 2. right? So the joint probability mass function, what is the joint probability mass function? So here this is x values, y values. So this is 0, 1, 2, and y is taking value 0, 1, 2. So for 0, 0 it is 0, this is 0, this is 1 by 4, this is 0, this is 2 by 4, 0, this is 1 by 4, 0, 0. So this is the joint probability mass function. Now, what is fx of x for this marginal density of x? So for this x, write fx of x here, and for y, write fy of y here. So this is fx of x, this is fy of y. Now, fx at x, this small x, capital X, it is taking three values. What are these three values? 0, 1 and 2. So when we substitute x is equals to 0, so this becomes fx at 0. So that means this is fx at 0. Then we have fx at 1 and then we have fx at 2. So when we are substituting x is equals to 0, that means corresponding to capital X, it is equals to 0. So we are taking, what is the formula for this? In case of a discrete, we are taking summation over y values, that is summation over y values of the joint probability mass function. When small x is equals to 0, summation over y values, that is y is equals to 0, y is equals to 1 and y is equals to 2. So simply add up these values. So at small x is equals to 0, corresponding to x is equals to 0, this becomes 0 plus 0 plus 1 by 4, this is 1 by 4. Then corresponding to x is equals to 1, summation over y values, this is 0 plus 2 by 4 plus 0, this is 2 by 4. Then corresponding to x is equals to 2, summation over y values, that is sum over y values, this is 1 plus 4 plus 0 plus 0, this is 1 by 4. Similarly, if we have to compute fy at y, so the formula for fy at y, this is sum over x values, that is summation over x values, f of x comma y. So for fy at y, summation over x values, that is at x is equals to 0, 1 and 2. So we'll take the sum over this column, that is 0 plus 0 plus 1 by 4, which is 1 by 4. Then 0 plus 2 by 4, this 0 plus 2 by 4 plus 0. So this is 2 by 4 and this is 1 by 4 plus 0 plus 0. So this is 1 by 4. So these are the marginal densities of x and marginal densities of y in the case of a two-dimensional discrete random variable. So how we write down the marginal densities of x and y? So simply, since x is taking values 0, 1 and 2, so the corresponding marginal density of x, that is corresponding to x is equals to 0, it is 1 by 4. So write it 1 by 4. Corresponding to x is equals to 1, this is 2 by 4, write it 2 by 4. And corresponding to x is equals to 2, write it 1 by 4. So this becomes 1 by 4. So and how we have computed the marginal densities? Simply take the summation over y values. Now for marginal density of y, so y is taking values 0, 1, 2. So write 0, 1, 2 and the corresponding marginal density. So this is fy at y. So taking the summation over x values, that is 0 plus 0 plus 1 by 4. So corresponding to y is equals to 0, this is 1 by 4. So write it 1 by 4. Corresponding to y is equals to 1, this is 2 by 4. Write it 2 by 4. And corresponding to y is equals to 2, this is 1 by 4. So write it 1 by 4. Now the next example, if x and y be continuous random variable with the joint probability density function. So this is joint probability density function. It is given by f of x comma y, which is equals to k. Here k is 1 by 240. Whenever x is in between 8.5 is less than equals to x is less than equals to 10.5 and y is 120 is less than equals to y is less than equals to 240 and this is 0 elsewhere. So this is the joint probability density function. So the question is, find the marginal density of x and y, that is fxx and fy at y. So for the marginal density of x, marginal density, that is fx of x, this is equals to, since it is a case of a continuous random variable, we'll use integration, and for marginal density of x will integrate over the y values, and here y is taking values 120 to 240. So this is 120 to 240. The joint function f of x comma y, this is 1 by 240. So this is 1 by 240 and integrate with respect to y. So this is coming out to be 1 by 240 and this is y, where the limits are 120 to 240. So this is coming out to be 1 by 240, and y, substitute y is equals to 240 minus 120, which is equals to 120 by 240, and this is equals to 1 by 2. So what is fx of x? Fx of x, this is equals to 1 by 2 whenever, because we have already substituted, this is the individual density of x. So this is 1 by 2, x is in between, 8.5 is less than equals to x is less than equals to 10.5. So this is the marginal density of x. Next, the marginal density of y. So fy at y will have to integrate over the x values. Here x is taking values from 8.5 to 10.5. So the marginal density, that is fy at y, integrate over x values, and the function, that is the joint density function, integrate with respect to x. So integrate, that is x is taking values from 8.5 to 10.5. The function, joint function, it is 1 by 240, integrate with respect to x. So this is coming out to be 1 by 240 x, and the limits from 8.5 to 10.5. So substitute x is equals to 10.5 and then 8.5. So this is 1 by 240, 10.5 minus 8.5. So this is 2 by 240, and the final is 1 by 120. So the marginal density of y, that is fy at y, this is 1 by 120 whenever y is in between 120 is less than equals to y is less than equals to 240. So this is the marginal density for y. Okay, so the next topic is independence. When can we say that the two random variables are independent? Since in this lecture we are dealing with two random variables only, so we will talk about the independence of two random variables here. So as we know that independence means that the value assumed by the one random variable, let it be x, it gives no information about the value assumed by the other random variable y. So if it gives no clue about the value assumed by the other random variable, then we say that the two random variables x and y are independent. Now, what is the condition to check for the independence of two random variables? So that means two random variables x and y are said to be independent if the said to be independent if and only if. So here this if and only if condition is important. That means this is the necessary and sufficient condition. That is the joint distribution, that is f of x comma y. This is the joint distribution of x and y. If it is equals to the product of the marginal density, fx of x into fy of y, then we say that the two random variables are independent. Now, what does this if and only if condition means? That means if the first statement, the statement 1 is two random variables x and y are independent, and the second statement is fxy, that is joint distribution, this is product of the marginal densities. So this is the second statement. So if and only if means that if statement 1 is true, then statement true second is also true, and if second statement is true, then statement 1 is also true. So if two random variables x and y are independent, then this condition will hold, and if this condition is true, then two random variables are said to be independent. So this is the condition for independence, to check whether the two random variables are independent or not. So we can check with this condition. Now look at the example one by one. So first example, suppose the random experiment, it is tossing of two coins. So this is the experiment, tossing of two coins, and the sample space for this random experiment, it is head head, head tail, tail head, and tail tail. This is the sample space, and x, it is taking values, sorry, x is denoting values number of heads, and y, it is number of tails. So x is assuming values 0, 1, 2, and y is assuming values 0, 1, 2. So what is the joint probability mass function for this? This is x, this is y. X is taking values 0, 1, 2. Y is taking values 0, 1, 2. Now, corresponding to this, x is equals to 0, y is equals to 0, their joint probability mass function, this we have already discussed in this video. So this is 0, 0, 1 by 4, this is 0, 2 by 4, and 0. This is 1 by 4, 0, and 0. So this is the joint probability mass function, and from this table we find out this fx of x, that is the marginal density of x and marginal density of y. So marginal density of x means summation over values of y. So that means at x is equals to 0, fx at 0, this becomes 0 plus 0 plus 1 by 4. This is 1 by 4, this is 2 by 4, this is 1 by 4. This we have already discussed in this video. And this is 1 by 4, 2 by 4, and 1 by 4. So these are the marginal densities. Now we need to check whether x and y are independent. Suppose that means this condition, that is for the independence, the condition is fxy at x comma y, this must be equals to fx at x multiplied by fy at y. So that means this joint must be equals to the product of marginal, and for this discrete and continuous, this must be true for all values of x and y. So the first, if we are taking it x is equals to 0 and y is equals to 0. So what is the joint distribution? This is f at 0 comma 0. This is the joint. So when x is 0, y is 0, the joint probability mass function, this is given by this 0. So this is the joint probability mass function. Now, what is fx at 0? That is the marginal density of x. What is x here? This x is 0. So marginal density of x at x is equals to 0. So marginal density of x at x is equals to 0, corresponding to x is equals to 0, marginal density is 1 by 4. So this is 1 by 4, and fy at 0, that is because here y is equals to 0. So fy at 0, this is corresponding to y is equals to 0, the marginal density is 1 by 4. So this is 1 by 4. So from these, that is f at 0 comma 0, this is not equals to fx at 0 multiplied by fy at 0, and hence the two random variables are not independent. So this condition must satisfied for all the possible values of x and y. Suppose if we are checking the values at this point, let the point is this one. Okay, so what is the joint distribution here? That is x is equals to 1 and y is equals to 1. So the joint probability mass function x1 and y1, this is given by 2 by 4. So this is 2 by 4. And what is marginal density of x at x is equals to 1? Because x is 1 here. So at x is equals to 1, this is 2 by 4. So this is 2 by 4. And fy at 1, this is equals to, that is fy at 1, this is equals to 2 by 4. So this is 2 by 4. So here f of 1 1, which is 2 by 4, and product of marginal is 2 by 4 multiplied by 2 by 4, which is coming out to be 4 by 16, that is 1 by 4. Again the product of, that is f at 1 comma 1, it is not equals to fx at 1 multiplied by fy at 1, and hence the two random variables are not independent. So if this condition it is not satisfied for a single case also, then we say that the two random variables are not independent. We need not to show for all the cases. If it is not satisfying for just a single case, then we need not to show for all the cases. So simply, if it is not satisfying for a single case, you can say that the two random variables are not independent. Now coming to the next example, suppose here we have X, which denotes the person's calcium level, and the capital Y, this denotes the person's cholesterol level. Okay, now here capital X, it is taking values from 8.5 is less than equals to X is this, and Y it is from 120 is less than equals to 240. This example for the probability density function case, this example we have already discussed. Now we need to check whether here the two random variables X and Y are independent or not. Now we know that f of x comma y, so the joint density function, this is 1 by 240 whenever x is in 8.5 is less than equals to x is less than equals to 10.5, and 120 is less than equals to y is less than equals to 240, and this is 0 elsewhere. So this is the joint density function, that is fxy for these values. Now we have already calculated fx of x. So this fx of x, uh, at the starting of this video, we already calculated the marginal densities of x and y for this function. So this is equals to 1 by 2, and x it is in between 8.5 is less than equals to x is less than equals to 10.5, and fy at y, this is coming out to be 1 by 120, where y it is in 120 is less than equals to y is less than equals to 240. So these are the marginal densities. Now check whether the two random variables are independent or not. Simply, what is f of x comma y? F of x comma y, this is 1 by 240. And what is fx of x? Fx of x, this is 1 by 2, and fy at y, that is the product of marginal. So this is fx of x and fy of y. This is 1 by 2 multiplied by 1 by 120, which is 1 by 240. So in this case, the joint distribution, this is product of marginal, and hence the two random variables are independent. So here x and y are independent. So in this way, we can check whether the two random variables are independent or not. Okay, so the next topic is the expectation. So whenever we have two random variables, how we compute the expected values. So for this, let x and y be two-dimensional random variables. So x, y, these both can be discrete, this both can be continuous. So, and their joint probability distribution or the density function, this is given by f of x comma y. So how we compute the expected value of a function of x and y? Let h of x comma y, this be some function of x and y. So h of x comma y, it is again a random variable. If it is a function of x and y, so it could be some random variable. The random variable, it could be x plus y, or it is xy, or it could be x square y square, or it is xy square. So this could be anything. So how we compute the expected value of this function, that is expected value of h of x comma y. So how we are going to compute this one? So if you remember, by definition of this expectation for the case of a single random variable, first we know how to compute the expected value. Expected value of a single random variable, that is expected value of x. If x is a discrete random variable, I'm writing discrete here. So if x is a discrete random variable, then we use summation. If x is continuous random variable, then we'll use integration. Whatever is written here, here we have x, so simply write it x here, x here. And whatever the density function of this random variable x, so this is fx of x, and here this is fx of x. Since we are using integration here, so integrate with respect to x over the possible values of x, and this is summation over x. Now if we want to compute expected value of x square, so x square, If x is discrete random variable, so in case of a discrete random variable, use summation. If x is a continuous random variable, use integration. So over possible values of x, over possible values of x, integrate. Now, whatever is written here, this is x square, so simply write it x square, here x square, and the random variable is x here, so take the density or the distribution function of this x, so this becomes fx of x dx. Here take the summation over this value, here take the summation over this value. In this way we can find out the expected value for a single random variable. Here we have a single random variable, that is x. Now if we have two random variable or a function of two random variable, that is x plus y, xy, x square, y square, xy square, then how we are going to compute the expected value? So just the first one, expected value, if we want to find out expected value of xy. So xy, this is equals to, because here we have two random variable, a function of two random variables, right? So that means we'll take summation if x and y are discrete. If it is discrete, then we'll use summation, and if it is continuous, then we'll use integration. So here we have two random variables x, so summation over x, summation over y. Instead of one, this time we have two random variable, so summation over x, summation over y. Whatever is written here, this is xy, so write it xy. And since here we have two random variables, so we'll have to take the joint function, that is the joint distribution function of xy. So this becomes f of x comma y. In case of continuous, integrate over the values of x, integrate over values of y. This is x plus y f of x comma y, that is the joint density function, and first integrate with respect to y, then with respect to x. You can change the order of integration as well, first with respect to x and then with respect to y. Accordingly the limits will be changed. Similarly, if we want to compute expected value of, let it be x plus y, so x plus y, this is again some other random variable function of xy. So if x plus y, it is a discrete case. So if it is discrete, then we have summation over x, summation over y. Whatever is written here, this is x plus y, so this is right x plus y, and the joint distribution or the joint density function, that is, this is we have fxy. So that is the joint function, it is f of xy. And if it is continuous, then integral over the x, integral over y. This function is x plus y, so write it fx x plus y, and the joint density function, that is, again this is, we have f of x comma y, integrate with respect to y first and then with respect to x. So in this way we can compute the expected value of a function of x and y, where the function, it is again a random variable. Now if x and y be two dimensional random variable, xy, this is a two dimensional random variable, and we need to compute the expected value of x. So if it is a two-dimensional random variable, so their joint probability distribution function, it is given to us, and we want to compute expected value of x, that is of a univariate function from this joint distribution function. So for this expected value of x, since it is a joint distribution function is given to us, marginal densities are not given to us. So from this joint distribution, we can easily compute the marginal densities. This we have already discussed in this video, that how to compute the marginal densities with the help of this joint density. So that means expected value of x, if x is a discrete, if this is discrete, if x is discrete and their joint function is given to us, so that means it is summation over x, summation over y. Because joint function is given, we are using the joint function f of x comma y, so we are taking summation over x values and summation over y values both. And what function is given to us? Here we have x only, so this is nothing but x. So this is equals to, since x, it is not depending on this summation of y values, so can we take this x outside of this summation? So this becomes summation over x, and this x as it is, then we can write this summation over y, f of x comma y. whenever x is discrete. I can take this x outside of this because this x, it is not depending on this sum over y values. Now we know that what is the marginal density of x. Whenever we need to compute marginal density of x using the joint probability mass function, this marginal density of x, it is the summation over y values and the joint probability mass function. So this becomes summation over y, fx of y, it is nothing but the marginal density of x. So we can write this thing as fx of x. So this becomes summation of x, this x multiplied by this thing is fx of x. So this is the formula for this expected value of x, and this is same as we did in the univariate case. That means for a single random variable case. Similarly, what is expected value of y? Expected value of y, it is summation over y values. Write this y as it is, and this is marginal density of y. So this is expected value of y, and if x and y are the continuous random variables. So if expected value of x, if x is continuous, so again we can compute the same way. Because x is continuous here, so we'll use integration. What is here? This is the function x. Write the marginal density of x and integrate with respect to x, and this is the x values. Similarly, expected value of y, this is going to be integrate over y. Write this y as it is, and this is fy at y, this is dy whenever y is continuous. So this is for the case of continuous. Whenever we have to find out the expectation, simply whatever is written here, write that as it is, and take the, if we have two random variables here, take the joint function. If we have a single random variable here, so take the marginal density function. So this is the way to compute the expected value. Now we'll compute the expected values with the help of an example. This will be more clear with the help of an example. So the first example, the same example we are taking for the discrete case, that the example of tossing of two coins. So this is the example, and we know the sample space here. So I'm simply writing where x denotes the number of head, y denotes the number of tail. It is taking values 0, 1, 2. It is 0, 1, 2, and their corresponding probabilities are 0, 0, 1 by 4. This is 0, 2 by 4, 0. This is 1 by 4, 0, 0. So this is the joint probability mass function. And from here, what is fx of x? This is 1 by 4, 2 by 4, 1 by 4. And what is fy at y? This is 1 by 4, 2 by 4, and 1 by 4. Now the first is, from here we want to compute expected value of x. So expected value of x, this expected value of x, this is equals to summation, right? Summation, because it is a discrete case, so we'll use summation. And over all the possible values of x, so here x is taking values 0 to 2. So x is going from 0 to 2. What is the function here? It is x, so write x as it is, and the marginal density of x is fx of x. So the first is, this is equals to x. When x is 0, substitute this small x as 0. So this becomes 0 multiplied by fx at 0. So this is fx at 0, plus then x is 1. So substitute x is equals to 1. So 1 into fx at 1, and the third is x is equals to 2. So this becomes 2 multiplied by fx at 2. So this becomes 0 multiplied by fx at 0. That is fx at x, this is the column for this. Fx at 0 is 1 by 4. So this is 1 by 4 plus 1. Fx at 1 is 2 by 4. So this becomes 2 by 4 plus fx at 2, this is 1 by 4. So this is 2 into 1 by 4. So this is equals to 0 plus 2 by 4 plus 2 multiplied by 1 by 4, which is again 2 by 4. So this is equals to 1. So expected value of x, this is equals to 1 here. Now we'll compute expected value of y. So here we are computing expected value of y. So expected value of y, this is equals to, again this is a discrete case, so we'll use summation. What is the function here? Y. So write y as it is, and the marginal density of y is fy at y. So summation over the possible values of y, and y is taking values from 0 to 2. Now when y is equals to 0, so substitute y is equals to 0. So this becomes 0 multiplied by fy at 0. What is fy at 0? This is 1 by 4. So write it 1 by 4 plus, then substitute y is equals to 1. 1 multiply, this is 1 multiply fy at 1. This is 2 by 4. So write it 2 by 4 plus, when substitute y is equals to 2, so this becomes 2 multiply fy at 2, which is 1 by 4. This is 1 by 4, so this is 1 by 4. So this is coming out to be, this is 0 plus 2 by 4 plus 2 by 4, and this is also equals to 1. Now the third case, if we need to compute expected value of xy. Here xy, this is a function of x and y, that is xy. So since we are using two random variable here, so we have to use the joint function instead of the marginal densities. So we'll take, because it is a discrete case, we'll take summation over x, summation over y. Now what is the function here? Xy. So write xy as it is, and their joint function, that is f of x comma y. So in this case, x is taking values from 0 to 2, and y is also taking values from 0 to 2. So we'll substitute values one by one. When x is 0, y is taking three values 0, 1 and 2. When x is 1, y is taking values 0, 1, 2, and when x is 2, y is taking values 0, 1 and 2. So substitute these values. So when x is 0, y is taking value 0, 1, 2. So the first is when x is 0 and y is 0. So 0 multiplied by 0. So this is 0 multiplied by 0, and their corresponding function is f at 0, comma 0. Then when x is 0, so this x is 0 and this y is 1. The corresponding probability, joint probability mass function is 0, 1. Then when x is 0, y is 2. So this is f at 0, comma 2, and multiply by this xy. So x is 0 and y is 2. Then the third one, when x is 1 and y is 0. So x is 1 multiply by y is 0, and their corresponding function is 1, comma 0. Similarly, when x is 1 and y is 1. So 1 multiplied by 1, because x into y, 1 multiplied by 1, and their corresponding function f at 1, comma 1, plus when x is 1, y is 2. So this becomes 1 multiplied by 2. Their corresponding joint probability mass function is f at 1, comma 2, plus when x is 2, y is 0. So that is because xy. So again we have to multiply x with y, and their corresponding joint probability mass function, that is f at 2, comma 1, plus 2 and 1. When x is 2, y is 1. So 2 multiplied by 1, and their corresponding joint probability mass function at f at 2, comma 1, plus when x is 2, y is 2. So this is 2 multiplied by 2, and their joint probability mass function is f at 2, comma 2. So now substitute this value. 0 multiplied by 0, and when 0 multiplied by the joint probability mass function, it is simply 0. So I'm simply writing 0, plus again 0 multiplied by 1, it is 0. So this multiplied by the joint probability mass function, it is again 0. So I'm simply writing 0 again. Then f at 0, comma 2. What is f at 0, comma 2? X is 0, y is 2. So f at 0, comma 2, it is 1 by 4. So this is 1 by 4, and 0 multiplied by 2, it is 0. So 1 by 4 multiplied by 0, it is again 0. So this is 0, plus 1 multiplied by 0, this is 0, and when it is multiplied by this joint probability mass function, it is 0 again, plus 1 multiplied by 1. This is 1 multiply by f at 1, comma 1. So what is f at 1, comma 1? X is 1, y is 1. So this is 2 by 4. So I'm simply writing this is 2 by 4. Then 1 multiply by 2. This is 2, and 2 multiply by f at 1, comma 2. So f at 1, comma 2, this is 0. So it is again 0. So this is 0, plus 2 multiplied by 1, so 2 multiplied by 1 is 2, and f at 2 comma 1, so 2 comma 1, this is this one, that is 0. So this is I have write written it twice, so this must be 2 multiplied by 0, this is 0. So 2 multiplied by 0, it is 0. And what is f at 2 comma 0? This is 1 by 4, so 0 comma 1 by 4 is 0 again. Then 2 multiplied by 2, this is 2, and f at 2 comma 1, this is 0, so this is 0 again, and 2 multiplied by 2, it is 4, and f at 2 comma 2, this is 0, so this is 0. So the final value, it is coming out to be 2 by 4. Next, if we want to compute expected value of x plus y, this time the function is x plus y, which is again a random variable. Again, here we have two random variables. So since it is a discrete case for this joint probability mass function, so we'll take summation over x values, summation over y values. So x is going from 0 to 2, y is going from 0 to 2. But this time, what is the function? Function is x plus y, so write down x plus y, and their corresponding joint probability mass function, this is f of x comma y. So first add the corresponding values, that is x and y values, and then multiply it with the joint probability mass function. So the first is when x is 0, y is 0, so 0 plus 0, because this time we have to add these two random variables x and y. So 0 plus 0, it is 0, and multiply by the corresponding probability mass function, that is f at 0 comma 0. So their corresponding probability mass function is 0 comma 0, which is 0, plus then x plus y. X plus y, this is 0 plus 1. So this is 1, and their corresponding probability mass function is 0. So 0 plus 1 is 1. Their corresponding joint probability mass function is 0. So write it 0, plus then when x is 0, y is 2. So 0 plus 2, this is 2, and multiply by the joint probability mass function, which is 1 by 4. So write it 1 by 4. Then plus we have x is 1, y is 0. So 1 plus 0, it is 1. Their corresponding joint probability mass function is 0. So that is, this is 0. Plus when x is 1, y is 1, and their corresponding joint probability mass function is 2 by 4. So 1 plus 1 is 2, and this multiply by 2 by 4. Then we have x is 1, y is 2. So 1 plus 2, it is 3, multiply by their joint probability mass function, which is 0. So this is 0, plus x is 2, y is 0. So 2 plus 0, it is 2, multiplied by their corresponding joint probability mass function, which is 1 by 4, plus 2 plus 1, that is when x is 2, y is 1. So this becomes 2 plus 1, 3, multiplied by the corresponding joint probability mass function, which is 0. So this is 0, plus when x is 2, y is 2. So 2 plus 2, it is 4, multiplied by their corresponding joint probability mass function, which is 0. Now solve this one. So 0 multiplied by 0, it is 0, plus this is again 0, plus this is 1 by 2. Then we have this is 0. Then this is 1. Then we have 0. This is 1 by 2. So this is 1 by 2, and these two are 0, 0. So that means this is simply 1 by 2 plus 1 by 2. This is 1 plus 1, that is 2. So expected value of x plus y, this is equals to 2. So this is how we can compute the expected values in the case of a discrete random variables when we have a ordered pair, that is x, y are both discrete random variables. Okay, so this is a question based on the joint probability density function. So there how we are going to compute the expected values. So in this case, x and y are taking values in an interval. Both x and y are the continuous random variable, and this is a function which is known as the joint probability density function, because here x and y are continuous random variable. So now for this case, how we are going to compute expected values. So first, if we are finding out the expected value of x. So expected value of x, we have already computed the marginal densities of x and y, where fx of x, this is equals to 1 by 2 where x is in between 8.5 is less than equals to x is less than equals to 10.5, and the marginal density of y, that is fy of y, this is equals to 1 by 120 where y it is in between 120 is less than equals to y is less than equals to 240. So these are the marginal densities. We have already computed these marginal densities for this particular density function in this in this video, in this lecture only, in the previous section. Now first we are going to compute this expected value of x for this joint probability density function. Since it is a case of a joint probability density function, here x and y are continuous, so we'll use integration because here we have one random variable. So what is the function here? That is x, so write x here. Okay, and random variable is x, so what is the density function, marginal density of x? This is fx of x, and integrate with respect to x. And what are the limits of this x? The limits of this x is 8.5 to 10.5, so write it 8.5 to 10.5. Integrate, so this is equals to 8.5 to 10.5, and we know that the marginal density of x, this is 1 by 2, so this is 1 by 2 into x, and integrate with respect to x, which is equals to x integration is x square by 2, so this is coming out to be 1 by 4 x square, and the limits from 8.5 to 10.5, so this is equals to 1 by 4. When we substitute x as 10.5, so this is 10.5 square minus 8.5 square. So here we can apply the formula of a square minus b square. So this becomes 1 by 4. So this is 10.5 minus 8.5 multiplied by 10.5 plus 8.5. So this 10.5 minus 8.5, this is equals to 2. So this becomes 1 by 4 multiplied by 2, and this is 0, 9, 19.0. So the final is 19 by 2. This is the expected value of x. So in this way we can compute the expected value of x. Now next we have expected value of y for the same joint probability density function. So since it is a case of a joint probability density function, here y, it is from the marginal density of y, fy at y, this is equals to 1 by 120, and y is going from 120 is less than y is less than equals to 240. So what is the function? The function is y, so simply write y and the marginal density of y, that is fy at y, and integrate with respect to y. The limits for this y, it is going from 120 to 240. So this becomes 120 to 240. This is y as it is. What is fy at y? This is 1 by 120, and integrate with respect to y. So this is coming out to be 1 by 120 as it is, and integration of y with respect to y, this is y square by 2, and this is 120 to 240. Substitute y is equals to 240 and then 120, so this becomes 120. We can take this 2 outside, so this becomes 240. When we substitute y is equals to 240, so this becomes 240 square minus 120 square. Again we can apply the formula of a square minus b square, which is equals to 1 by 240, and this is a plus b and a minus b, so a minus b is 120, a plus b, this is 360, and this is equals to 180. So expected value of y, this is equals to 180. Now for the given probability, joint probability density function, that is this function, will compute expected value of xy and expected value of x plus y. So first we'll compute expected value of xy. So for this expected value of xy, this time we have a function of x and y. So this is again a random variable xy. So because it is a case of a joint probability density function, here we'll use integration, integral over x and y, because here we have two random variables. So integral over possible values of x, possible values of y, whatever be the function here. The function is xy, write xy as it is, and their joint probability density function, that is fxy. So first inner is for the y. So first integrate with respect to y and then with respect to x. Now the joint probability density function, this is 1 by 240. Limits for x is 8.5 to 10.5, y is 120 to 240. So this is integral over limits for x is 8.5 to 10.5, limits for y this is 120 to 240, x, y as it is, and their joint density function this is 1 by 240. This is integrate with respect to y, then with respect to x. So since it is a constant, so we can take it as 1 by 240 outside of these integrals. So first integrate with respect to y, so 8.5 to 10.5 as it is. Okay, so integral of this xy. So first I'm writing this as it is, that is 120 to 240. This xy integrate with respect to y first and then with respect to x. So this is equals to 1 by 240. And this x limits 8.5 to 10.5. So first integrate with respect to y. So x, because we are integrating with respect to y, so treat this x as a constant. So write this x as it is. Integration of y with respect to y is y square by 2. So this is y square by 2. Take the limits of y as 120 to 240 and then integrate with respect to x. So this is equals to 1 by 240. When we substitute y is equals to 240 and then 120, so this integral 8.5 to 10.5, x as it is, substitute, take this y outside of this integral, so this becomes 240 multiplied by 2, so which is equals to 480. So I'm writing 480, taking this 2 multiply by this. Now x as it is, substitute y is equals to 240, so this becomes 240 square minus 120 square, and then integrate with respect to x. So 240 square minus 120 square. So again we can use a square minus b square, a minus b which is 120, a plus b which is 360. So we can take this 120 into 360 outside. So this becomes 120 multiplied by 360, because this is a constant term, divided by 480, and then integrate with respect to x. So that is when we integrate with respect to x, so this becomes x square by 2 and the limits from 8.5 to 10.5. So the calculations are quite complex, but still this is 0, 0, 12, 1, 12 fours are 48, and this is equals to 90. So this one is 90. When we substitute x is equals to 10.5, so again we can use 10.5 square minus 8.5 square, and this 2 outside of this, so this is equals to 45 multiplied by a square minus b square again, so a minus b, it is 10.5 minus this, that is 2, and 10.5 this, it is 90. So simply multiply 45 to the 90, and this 45 to the 90, this is 1710. So that means it is equals to 1710. So this is the expected value of xy. Now next we can compute the expected value of x plus y in this similar manner. So expected value of x plus y, again here we have two random variables. So first we'll integrate with respect to x, then integrate with respect to y. So the limits for x is 8.5 to 10.5, limits for y is 120 to 240. The function here is x plus y, and their joint function, this is joint probability density function, this is 1 by 240, and then integrate with respect to y first, with respect to x then. So you can change the order of integration as well, first with respect to x and then with respect to y. Accordingly the limits will be changed. Now this is equals to, we can take this 1 by 120 outside of this. Now integrate with this function. So this is integral 8.5 to 10.5 as it is, integrate with respect to y. So when we integrate x, because x is a constant, so integration of a constant function with respect to y, this is xy. plus integration of y with respect to y, this is y square by 2, then take the limits as 120 to 240. Then substitute y is equals to 240 and then 120. So this is equals to 1 by 240 integral 8.5 to 10.5, and substitute y is equals to 240, so this becomes 240x, then we have 240 square by 2, then minus 120x minus 120 square by 2, then integrate with respect to x. Again, when we combine these two terms, so this is equals to 1 by 240 as it is, integral from 8.5 to 10.5. So first combine these two terms, so 240x minus 120, it is 120x, and this is the constant term, that is 240 square by 2. So here the LCM is 2, and first we'll again we can use the formula a square minus b square. So this is 240 plus 120 and 240. So this is 120 multiplied by 360 and this divided by 2, and then integrate with respect to x. So this is coming out to be 60. So now this is equals to 120. When we integrate this function with respect to x, so this is coming out to be 120 x square by 2 plus, here we have, this is 21600 x, because we are integrating this function with respect to x, so this is this, and substitute x is equals to 8.5 to 10.5. Then when we substitute x is equals to 8.5 to 10.5, so this is equals to 1 by 240 as it is. Okay. Here x is equals to 10.5, and when we substitute x is equals to 8.5, so 120 by 2, so this is 60 only. So we can write this as 60. So this is 10.5 square minus 8.5 square. So one term is this one. So from here again we can apply the formula, and for this second term we can take the common 21600, and 10.5 minus 8.5, this is simply 2. Now if we solve this, so this is, will take the next page. So this is equals to 1 by 240, then we have 60, then we have 10.5 square minus 8.5 square, then plus 21600, and this multiply by 2. So this is the final. So this is 1 by 240. Again we can use a square minus b square, so which is equals to a plus b and a minus b, which is 19, and a minus b, this is 2, plus this is coming out to be, this is 3, and this 43200. So the calculation is quite complicated. So this is 120 multiplied by 19 plus 43200. So I think we can take 120 common from this one. So this is this 0 cancels out from here. So this is simply 1 by 24. This is 19 into 12, that is 12 into 19 plus 432. So the final answer is, this is 0. So it is coming out to be 189.5. You can use calculator for this one. So this is coming out to be 189.5. So in this way, we can compute the expected values for both the, if xy is a two-dimensional discrete random variables or a continuous random variable, if the joint probability mass function or the density function is given to us. So we can compute the expected value in this way. Okay, so the next topic, it is the covariance. Covariance basically tells you the measure of how much two random variables x and y vary together. So this tells you the measure of how these two random variables vary together. So now what is the covariance? Suppose we have two random variables x and y with their respective means as x bar and y bar. Here x bar and y bar, they are the mean of x and y respectively, or we can write this x bar as expected value of x, and y bar as expected value of y. In other way, we can denote this expected value of x as mu x or mu y. So what is the covariance between x and y? Covariance of x, y, this is given by expected value of x minus x bar multiply by y minus y bar. This is the covariance formula, and the computational formula that we used for the computation purpose, this is given by covariance of xy, which is equals to expected value of xy minus expected value of x into expected value of y. So this formula we use for the computational purpose. So whenever we have to find out the covariance, we use this formula. And this is the definition of the covariance. So this is the formula, expected value of x minus y bar, x bar into y minus y bar, where this x bar and y bar, it denotes the respective means of x and y. Now, we'll derive this formula, that is the computational formula, by the actual definition of the covariance. So we'll start with this one. So what is covariance? By the definition of covariance, that is covariance of x, y, this is nothing but expected value of x minus x bar into y minus y bar. Now simply solve these brackets. So this is expected value of x, y minus x, y bar minus x bar y plus x bar y bar. So the first property that we are going to use here, that is the first expected value property. The property is expected value of x plus y. This is same as expected value of x plus expected value of y. So using this property, we solve this. So this becomes expected value of xy minus expected value of x y bar minus expected value of x bar y plus expected value of x bar y bar. So then we know that this y bar, x bar, this x bar, y bar, they all are means of x and y. So that means these means are the constant function. So that means the second property that we are going to use, that expected value of a constant, this is simply equals to constant. Like what is the expected value of 1? Here 1 is constant, so this is equals to 1. Expected value of minus 3. Minus 3 is a constant, so this is equals to minus 3. So since y bar, x bar, y bar, they are representing the mean here, denoting the mean of x and y. So these are the constant. So we'll take this out. And the third property, so this is the second, and the third one, expected value of c into x. If a random variable, it is multiplied by some constant, this is same as c into expected value of x. So these three properties that we are going to use here, the first one is this one, second one is this one, and the third one is this one. So here this expected value of xy as it is. So this xy as it is. Then here y bar is constant and x is a random variable. So we can take this y bar constant outside of this. So this becomes y bar expected value of x minus this x bar is a constant. So this becomes x bar into expected value of y. And here both x bar and y bar is a constant. So that means expected value of a constant is constant. So this becomes x bar y bar. And what is this x bar y bar? X bar y bar, it is nothing but the expected values, that is the mean. So we can write this as expected value of xy minus y bar. What is expected value of x? This is the mean, so we can write this as x bar minus x bar. What is expected value of y? Mean, so this is y bar plus x bar y bar. Now cancel these two terms and we are left with expected value of xy minus what is x bar? X bar is expected value of x, and what is y bar? Y bar is expected value of y. So this is the computational formula for the covariance, how to compute the covariance between x and y. So this is the computational formula, that is covariance of x, y. Now for the first example, how to compute the covariance, we have a probability density function, that is fxy, which is equals to 1 by 240, where x is in between 8.5 is less than equals to x is less than equals to 10.5, and y, it is from 120 is less than equals to y is less than equals to 240, and this is 0 elsewhere. So for this joint probability density function, we have already computed the expected value of x, which is equals to 19 by 2, expected value of y, which is equals to 180, and expected value of xy, which is coming out to be 1710. So now for this case, what is the covariance? Covariance of xy, this is equals to expected value of xy minus expected value of x into expected value of y. Simply substitute these values. So this is 1710 minus 19 by 2. So it is 9.5 multiplied by 180. So this is equals to 1710 minus 1710, which is equals to 0. So that means covariance of xy, it is equals to 0, and for this case we have already seen that the two random variables x and y are independent. So from here we can also see this, that if x and y are independent, so this implies that covariance of xy, this is also equals to 0. So if x and y are independent, you can directly say that covariance of xy is equals to 0. But this is not the converse condition. That means in converse condition, it is not true that if covariance of xy is equals to 0, you cannot say that the two random variables x and y are independent. But one way it is true, if the first statement is true, that is if x and y are independent, then covariance is 0. But if covariance is equals to 0, you cannot say that x and y are independent. For the second, where we have the random experiment of tossing of two coins. So for this case, tossing of two coins, for this case we have computed the expected value of x, which is equals to 1, expected value of y, this is also equals to 1, and expected value of xy, this is equals to 1 by 2. So this we have already computed. So from here, covariance of xy, this is expected value of xy minus expected value of x into expected value of y. So this is equals to 1 by 2 minus 1 into 1, which is nothing but minus half. So here covariance of xy, it is equals to minus half, which is not equals to 0. So also one other remark, that is, the remark is, like if we have first statement that if x and y are independent, if x and y are independent, this implies that covariance x comma y, it is equals to 0. And on the other way, we can say that if covariance of x, y, it is not equals to 0, then x and y are not independent. So these two statements are true, that if first statement x and y are independent, then covariance between them, it is equals to 0. But if it is not equals to 0, if covariance is not equals to 0, then we can say that x and y are not independent. But if we have covariance of x comma y is equals to 0, we cannot say that x and y are independent. They can be independent, they cannot be independent. So this is not the converse statement, but from here we can conclude that if covariance is not equals to 0, then x and y are not independent. So in this case, if you look at this, that covariance is not equals to 0, then we can say that the two random variables are not independent. So these are the two questions for practice. The first one, it is based on the concept of a joint probability density function, because here both x and y, they are taking values in the interval. So it is a question based on this. So x and y are continuous random variable. So this is a question. And the second question, it is based on the joint probability density function. So please do these, joint probability mass function. So please do these questions. So if you have any queries, you can write down your queries at my mail ID. I will share my mail ID in the description box. Hope you understood the concept of the joint distribution clearly. Hit like if you like this video, share and subscribe to my channel. Thanks for watching.